Okay, welcome back. We're going to continue with our reaction energy chapter, and today we're going to talk about the spontaneity of a reaction. So you'll see at the top of your notes it says spontaneous reactions. Let's first talk about this word spontaneous. In the context that we're using it here, it means that reactions can occur without the continuous input of energy. For instance, if I have a barrel of gasoline and I throw a match in it, that gasoline will continue to burn without me having to continually add more matches until the gasoline is consumed. That's spontaneous. However, non-spontaneous reactions cease or stop as soon as I stop adding that energy. For instance, if I wanted to separate water into hydrogen and oxygen gas by passing an electric current through a water solution. When I turn the switch on and electricity passes through the water solution, I can see hydrogen gas and oxygen gas bubbles forming as I decompose the water. But as soon as I turn that switch off, the reaction stops. So that's a non-spontaneous process because I have to continually add energy for that reaction to occur. Now, nature tends to move in two directions spontaneously. The first direction it tends to move spontaneously is to lower energy. That means delta H is negative. Recall that's an exothermic direction. So, for instance, let's use this analogy. If I take a bicyclist and put him right in the middle of a hill and let him go, what's he going to do spontaneously? Is he going to move up the hill spontaneously? Of course not. He's going to have to pedal like crazy to go to the top of that hill. He will move downhill spontaneously, from high energy down to low. Delta H is negative. That happens with chemical reactions as well. Nature prefers lower energy molecules as opposed to high energy. So the high energy molecules will release energy and become low energy molecules spontaneously. The other direction nature tends to go towards spontaneously is to a higher degree of disorder. Now, the degree of disorder of something is called the entropy, and it's symbolized with the letter S. So nature prefers a higher degree of disorder. Delta S is positive, a higher entropy. So the change in entropy is positive. Let me show you what that means. Here are two pictures of my sock drawer. My sock drawers rarely look like this. In fact, I had to arrange it like this and spend lots of time and energy to make my sock drawer look like this for the picture. I have the lighter colored socks folded into the left, and the darkest color socks, of course, folded into the right. Normally, and understandably, my sock drawer looks like this. And you can understand why. Yours probably looks the same way, because it's easier to have a disordered situation than an ordered situation. The same thing is true in chemistry. Nature prefers a greater degree of disorder. For instance, if I had a solid and a liquid and a gas of the same substance, the entropy would increase when I go from a solid to a liquid to a gas. So we'd have an increase in entropy. Delta S would be positive as we move from a solid to a liquid to a gas. Think about this. Aren't solid particles crystalline? They are locked next to each other and they vibrate back and forth. They form a nice, pretty crystalline structure. Liquid particles can slide past each other in all directions. So they're still relatively close to each other, but they can move past each other. They are more disordered. And of course, as you guys know, gases occupy the entire volume of their container. It's the most disordered system. So gases, a gas phase of a substance has a much higher entropy than the liquid, which has a higher entropy than the solid phase of that substance. Well, let's give an example of a process. Let's take the melting of ice. That seems pretty simple. Does ice melt spontaneously? That means we're going to go from solid water to a liquid water. Well, let's decide. Is this an endothermic or exothermic process? Does it take energy to melt ice, or does it give off energy when ice is melted? Well, we have the solid particles. We're trying to turn them into liquid particles. We're trying to get them to move past one another. Won't that take energy? Delta H is positive when you go from a solid to a liquid. What about the entropy change? Doesn't a liquid have more disorder than a solid? So when I go from a solid to a liquid, entropy is increasing. Delta S is positive. So, will this reaction proceed spontaneously according to the two criterion above? Well, there's a question mark there, and I'm going to put it here again. We don't know, because in this case, temperature is going to play a role. We know that ice does melt spontaneously at room temperature. We also know that below 0 Celsius, it does not melt spontaneously. So oftentimes, in a reaction to determine its spontaneity, we need to know the temperature. Now, to help us along, I'm going to give you a new magic formula. This magic formula is of great importance. It's called the Gibbs Helmholtz equation. Delta G equals delta H of a reaction minus T delta S of the reaction. Of course, delta S of the reaction is the change in entropy. T is our Kelvin temperature. Delta H is the enthalpy of the reaction. And delta G, that's the new one, is called the free energy of a reaction. Now it turns out, if delta G is bigger than 0, that means it's a positive number, the reaction's considered to be non-spontaneous. Delta G is positive, the reaction turns out to be non-spontaneous. If delta G is less than 0, or has a negative value, the reaction is said to be spontaneous. And then finally, what if delta G is neither negative nor positive? What if it's 0? Well, we don't worry too much about this situation this year. We worry about a lot more next year in AP. But for right now, in the example we're going to do, I'll show you that when delta G is 0, the reaction is said to be at equilibrium. You remember that word, don't you? All right, so back to our water example. We're taking water that's a solid and turning it into a liquid. Let's find delta G for this reaction. We'll find its sign. I first want to do it at 20 degrees Celsius. Now, I've found the heat of this reaction for you and the entropy of this reaction, so we should be able to calculate the free energy of the reaction. Now, one thing you have to worry about is the heat of the reaction is often given in kilojoules. And the entropy, when you look these up in data tables, for some reason they like to put it in joules per mole Kelvin. We have to make these units the same. So isn't 21.99 joules per mole Kelvin the same as 0.02199 kilojoules per mole Kelvin? So we're going to use that number here in just a second to calculate delta G. So delta G, remember, equals delta H minus our Kelvin temperature times delta S. And these are for the reactions. So let's plug and chug. The delta H of my reaction to find delta G of the reaction is positive 6.01 kilojoules per mole minus T. Now my temperature is 20 Celsius. That's 293 Kelvin times delta S of the reaction, and we're going to use 0.02199, so I have kilojoules per mole Kelvin over here. So let's see what we end up with here. We have 6.01 minus, and we're going to use our parentheses key quite a bit today, so parentheses 293 times 0.02199. We'll close off those parentheses and hit enter. And my value here is a negative 0.433 kilojoules per mole. Now the important thing here is this negative sign. That tells us that at 20 degrees Celsius the reaction is spontaneous. Delta G is less than 0. Well, let's do it at negative 20. And we probably already know the answer to this. Is ice going to melt spontaneously at a temperature that cold? Of course not. So we know that delta G is going to end up having a positive value here. But let's do it. Delta G of the reaction is still positive 6.01 kilojoules per mole minus, now my temperature is changing to negative 20. So that would be 253 Kelvin times 0.02199 kilojoules per mole Kelvin. And let's see what we end up with here. 6.01 minus, my parentheses key, 253 times 0.02199. And I end up with a positive number this time. Positive 0.447 kilojoules per mole. Now the important sign here is the positive sign, and that tells us that this is non-spontaneous. Okay? So, of course, ice does not melt spontaneously at that low of a temperature. Now, just for fun, let's do 0 Celsius, because we know that at 0 degrees Celsius, water's at its freezing or melting point. It's doing both at the same rate, so it's at equilibrium. So when I do this, delta G will be pretty close to 0. So let's do it at 0 Celsius. Delta G of the reaction equals positive 6.01 kilojoules per mole minus, now we're at 273 Kelvin, times 0.02199 kilojoules per mole Kelvin. And we should get an answer pretty close to 0. I did round off my temperature to the nearest whole number, so we could have a little rounding issue. The last digit might not be 0, but let's see what it is. 6.01 minus 273 times 0.02199, and I end up with 0.007, which I'm going to say is pretty doggone close to 0, which means that this reaction is at equilibrium. So that temperature tells us it's melting and freezing at the same rate. Okay? Now, we're going to take a little divergence from your notes here. I'm actually going to skip example 7 this year. So when you look at it in class, you'll notice that we'll skip it in class as well. Let's not worry about this. Instead, I'm going to do some examples from your textbook in just a few minutes for you. So let's skip to the last page. Whoops, where did that go? Of your notes. Oh, sorry for the disarray here. Here we go. It's this chart for us. Now this is sort of an important chart, and pay close attention to this now. I'm going to switch values of delta H and delta S, and we'll determine spontaneity. If delta H is negative, remember, at the beginning of this video, nature prefers that. If delta S is positive, nature prefers that as well. So whenever delta H is positive for a reaction, and delta S is positive for a reaction, delta G will always be negative, which means that regardless of the temperature, the reaction is always going to be spontaneous. Now let's think about the opposite of that. Nature does not like a positive delta H. That's endothermic. That's going uphill. Nature does not like a negative entropy. That's becoming less disordered. Nature doesn't like that either. So that combination will always give us a positive delta G, which means the reaction will be non-spontaneous at all temperatures. The third example is like the one we just did with water melting. Delta H was positive, which nature doesn't like. Delta S was positive, which nature does like. So they're fighting each other here. These are temperature dependent, so delta G could be positive or negative. Turns out that at higher temperatures they're spontaneous, and at lower temperatures it's non-spontaneous. So these are temperature dependent when delta H and delta S are positive. Now the last scenario is when we have an exothermic reaction, which nature likes, and getting less disordered. That means more ordered, by the way, which nature doesn't like. Once again, delta G could be positive or negative. So these are also temperature dependent. These turn out to be spontaneous at low temperatures and non-spontaneous at high. So it turns out when the signs of delta H and delta S are the same, those reactions are temperature dependent as far as their spontaneity is concerned. When the signs are opposite, delta H is negative, delta S is positive, those are always spontaneous, or delta H is positive and delta S is negative, those are always non-spontaneous. Okay, well, let's take a look at a problem from our textbook. And this will be, let's see, similar to your homework, if not identical to your homework tonight. Let's do number 25. Let's see if we can get that here on the camera. Number 25 from your textbook on page 553. So in this example, the heat of the reaction is negative 76 kilojoules. The entropy is negative 117 joules per Kelvin. And we're going to find delta G and find out if that reaction is spontaneous or not. Notice the sign for delta H and delta S are both negative, so this is one of those temperature-dependent reactions. So let's put this aside. We'll get our paper back in view here. And this will be number 25 from page 553 of your text. So once again, delta H is a negative 76 kilojoules. Delta S is a negative 117 joules per Kelvin. The temperature, let's put that right here, is equal to 298.15 Kelvin. And our job is to find delta G and determine whether or not the reaction's spontaneous. So, if you want, you can pause the video and try this on your own, and then come back and press play and see how you did. So I'll give you a second to do that. Okay, here we go. Doesn't delta G of a reaction equal the delta H of the reaction minus T delta S of the reaction? Our favorite Gibbs Helmholtz equation. So let's see what we get. Delta H is a negative 76 kilojoules minus, my temperature is 298.15 Kelvin, times my delta S. Now remember to be careful, and I hope you remembered when you tried this on your own. Delta H is in kilojoules, delta S needs to be in kilojoules as well. So this will be a negative 0.117 kilojoules per Kelvin. Okay, hopefully you remember to do that. So, let's see what we get here. We have a negative 76 minus, our parentheses key again, 298.15 times a negative 0.117. And I end up with a negative, looks like I'm only allowed to go to the nearest whole number here, negative 41 kilojoules. So we have the value of delta G. Now we have to tell whether this is spontaneous or not. Now since that sign is negative, think it is a spontaneous reaction. So I have enough heat that's generated to compensate for the lower degree of disorder that's happening here. And so that extra heat will allow this reaction to be spontaneous. Should we do another one? Yeah, let's do another one. Let's see, we just did number 25. So let's do one of them from number 27. Now if I could just read this off to you, instead of trying to get the book in here again. Number 27 is very similar to what we just did. It gives us, this is 27A we're going to do, it says the delta H of a reaction is positive 125 kilojoules per mole, and the entropy of this reaction is 0.0350 kilojoules per mole Kelvin. Isn't that nice? That's in kilojoules for you. the temperature of this reaction is 293 Kelvin, and we are asked again to find the free energy of this reaction and then to determine the spontaneity. So once again, pause the video, try it yourself. Okay, we're back. Let's see what we end up with. Delta G of the reaction equals delta H of the reaction minus T delta S of the reaction. Delta H is a positive 125 kilojoules per mole minus my temperature, which is 293 Kelvin, times 0.0350 kilojoules per mole Kelvin. Now you'll notice delta H is positive, delta S is positive. They have the same sign, which means these are temperature dependent as far as their spontaneity is concerned. So let's see what we get here. 125 minus 293 times 0.0350, and I end up with 115 kilojoules per mole. Now that obviously is a positive 115, so that tells us the reaction is not going to be spontaneous. Okay? Alright, that should give you a good head start on your homework tonight, and a couple of practice problems on using the Gibbs Helmholtz equation. Now there are other practice problems in your book that I encourage you to look at and use to help you with your homework. So sorry this went a bit long, but we've wrapped up the chapter. Thanks, and we'll see you next time when we'll be starting a new chapter.